Welcome back. This is an Aleks homework video on calculating the pH of a weak acid titrated with a strong base. Okay, imagine putting some acid and bases together in a jar. If you've got more moles of base, it's going to eat up the acid, neutralize the acid, and you'll have base left over. If you have more moles of acid, it'll eat up the base and you'll have more moles of acid left over. If they're exactly the same, if they have the same amount of canceling power, then you'll only end up with some salt in the water. Okay, so those are your three possibilities. So the first thing you're going to do is find out, you're going to take the amounts that they give you and the molarities that are given, and then you're going to figure out from there how many moles of acid and how many moles of base. When you look at the balanced equation, you'll be able to tell, is it a 1-to-1 relationship, is it a 2-to-1 or a 2-to-3 or some kind of relationship, and then you'll be able to know what the canceling power of the acid and the base, the neutralizing power, is. Okay? So it would be awesome if you could have a 1-to-1 relationship in the balanced equation. That makes it the easiest. We'll see what we have here. So I've got some cyanic acid and I've got some sodium hydroxide. So sodium hydroxide is a strong base and it's going to completely dissociate. The cyanic acid is weak, so it's not going to totally dissociate, but the acid can eat it up if there's enough. So let's put it together and see what we can find. So I wrote out the balanced equation. And in this case, it was a 1-to-1 relationship. I love it. So since it's a 1 acid to 1 base relationship, so I've got, for every mole of hydroxide that is neutralizing the acid, I've got one mole of the cyanic acid to neutralize. Okay, so I simply took the amounts and divided them out. Now, remember that molarity is moles over liters. Okay, so when you're given a molar solution, that's moles over liters. They're giving you milliliter amounts. So I'm not going to be tricked by that. I'm going to put it into liters and then take those moles and divide by liters, or in this case, multiply by liters to get rid of it. And I've got in red here 0.077 moles of acid and 0.090 moles of base. That means I have leftover base. All my acid's been used up. I have leftover base in the water, and that base is going to have a high pH. So my guess, it's going to be 10, 11, 12, probably 11 or 12, okay, because sodium hydroxide is a very strong base and it's used up all the acid and then left over in the water. So you're going to have a very basic solution left over. So I subtracted them and found out how many moles that I have, and now I need the molarity. So here is a problem. I remember this problem, not this exact problem, but when I was learning, I would always be tricked by dividing by the moles of base that was given, and I'd get the answer wrong. Remember, if you're adding acid and base together, you have the volume is both of them together. So it's the total volume of the acid and the base. So remember, they need to be in liters, but whatever the moles of acid, or the liters of acid and the liters of base together, that's what you're going to divide by. So I have the moles of base, moles of the hydroxide, divided by the total liters of the acid and base that was put, and I have a hydroxide concentration, molar concentration of 0.029. Now, if I was asked for the pOH, I would just take the negative log of that and I'd be done. But I'm asked for the pH, okay, which means I need one more step. The water constant, or the water dissociation constant, it's a constant. It's 1.01 times 10 to the negative 14 molarity squared all the time. And I know that the molarity of my acid times the molarity of the base equals this constant. So I'm simply going to, in my case, divide by the hydroxide, because that's what I know, and find the acid concentration. So when I do the division, I get a concentration in molarity in molar concentration of 3.46 times 10 to the negative 13. Now that makes sense because it's going to be very, very high pH. It's lots of hydroxide. So I'm not going to have a low molarity. I'm going to have a very, tiny, tiny molarity. Or I'm not going to have a high molarity. I'm going to have a tiny. So this is negative 13. Very, very small amount. Doesn't matter because that's the molarity of the hydroniums. So I'm going to take the negative log of that and take it to 2 decimal places, 12.46. Okay? Pretty straightforward question. I hope that helps.